Do you still remember when a polygon is placed inside a circle? That is, the vertices of the polygon touch the circumference. What do we call this circle? You are correct. It is a circumscribed circle. In a previous program, we discussed the properties of the arc, chord, and angle of a circle and the theorems. Now, let's discuss the properties and theorems of a cyclic quadrilateral. In this cyclic quadrilateral, angle A and angle C are opposite angles. Also, angle B and angle D are a pair of opposite angles. Let's discuss the relations between opposite angles in a cyclic quadrilateral.
Angle A and angle C add up to 180 degrees. Angle B and angle D also add up to 180 degrees.
Based on these results, what conclusion can we draw?
According to the two theorems, that the angle at center is twice the angle at circumference and angles at a point. The sum of a pair of opposite angles of a cyclic quadrilateral is 180 degrees. The theorem is opposite angles, cyclic quadrilateral.
Let's take a look at the circle again. If we produce the side DC to a point E, which is outside of a circle, angle ECB is called an exterior angle of a cyclic quadrilateral. And angle A is the interior opposite angle corresponding to angle ECB.
Since angle ECB and angle BCD add up to 180 degrees, angle BAD and angle BCD are also equal to 180 degrees as proven previously. Therefore, angle BAD is equal to angle ECB. The theorem is, the exterior angle of a cyclic quadrilateral is equal to its interior opposite angle.
When there are some points which lie on the same circle, these points are said to be concyclic.
That means A, B, C, and D are concyclic points.
Supposedly, there are two distinct points. How many circles can we draw passing through these 2 points? For the 2 points A and C, we can always draw more than one circle passing through them. How do we draw them?
We join these 2 points by a straight line. And then draw a perpendicular bisector. Choose any point lying on the perpendicular bisector as the center, as OA and OC will be the radius. Then more than one circle can be drawn through the points A and C.
So we are certain that any 2 distinct points are concyclic. If 3 distinct points are on a circle, are these 3 non-collinear points always concyclic? For the 3 points A, B, and C, if a circle can be drawn passing through these 3 points, then these 3 points are concyclic. Can that be drawn?
These 3 points are joined and a triangle is formed. We construct the perpendicular bisector of 3 sides of the triangle. These 3 perpendicular bisectors intersect at a point. Use this point as the center. Then OA, OB, and OC become the radius. Then the circle can be drawn passing through these 3 points A, B, and C. These 3 non-collinear points are concyclic.
We discovered that the vertices of the triangle are concyclic, and the circle passing through these 3 points are called concyclic triangle.
The theorem is, any 3 points not on the same line must be concyclic. And there is one and only one circle can be drawn passing through these 3 points.
After having talked about 2 and 3 distinctive points are concyclic, then is it true for 4 non-collinear points to be concyclic? For the 4 distinct points A, B, C, and D, if a circle can be drawn passing through these 4 points, then these 4 points are concyclic. Can this be drawn?
If the 4 points are joined and a quadrilateral is formed, then if the perpendicular bisector of each side of the quadrilateral intersect at a point, then a circle can be drawn, and hence these 4 points are concyclic.
In fact, not all quadrilaterals are cyclic quadrilaterals. In order to determine a given quadrilateral is a cyclic quadrilateral, 3 separate theorems will be used.
If angle APB and angle AQB are equal angle on the same side of AB, then points A, B, Q, P are concyclic. The theorem is the converse of angles in the same segment. If the sum of angle BAD and angle BCD is equal to 180 degrees, or the sum of angle ABC and angle ADC is equal to 180 degrees, then the 4 points A, B, C, and D are concyclic. The theorem is opposite angles supplement. If an exterior angle of the quadrilateral is equal to the interior opposite angle of a quadrilateral, then the 4 points A, B, C, and D are concyclic. The theorem is the exterior angle is equal to the interior opposite angle.
We have discussed 2, 3, and 4 distinct points are concyclic. Whether 5, 6, and more points are concyclic, we leave these for you to find out. This is a V-shaped rod, and now the circle is placed inside it, with the circle touching 2 points of the V-shaped rod. This is to say that the 2 straight lines touch the circle separately. According to definition, these 2 lines are the tangents to the circle.
We are now going to discuss the properties of the tangent to the circle and the related theorems. If a straight line is the tangent to the circle at a point, then the tangent is perpendicular to the radius. The theorem is tangent perpendicular to radius.
If we look at this the other way around, if a straight line is perpendicular to the radius of a circle, then this straight line is the tangent to the circle.
The theorem is converse theorem of tangent perpendicular to radius.
Based on these 2 theorems about tangent and radius, we have the following deduction.
In the circle, there is a tangent. At the point of contact, there is a perpendicular line. This perpendicular line passes through the center of the circle. The theorem is the perpendicular to a tangent at its point of contact passes through the center of the circle.
Have we noticed that for these 2 tangents, the intersecting point and the point of contact are of equal length? As for any point outside a circle, we can draw 2 tangents to the circle. The distance from this external point to the point of contact are the same. The above property is in fact a theorem.
If tangent TP and TQ intersect at point T, then the length of TP is equal to length of TQ. Angle POT is equal to angle QOT. Angle PTO is equal to angle QTO. The theorem is tangent properties.
After discussing the properties of circle and tangent, let's take a look at this circle.
There is a tangent PQ to the circle. From point of contact T, a straight line TA is drawn to the circumference. Chord AT and the tangent form an angle ATQ and angle ATP.
These two angles are called tangent chord angles. Chord AT divides the circle into two segments. Segment ABT lies on opposite side of angle ATQ. It is the alternate segment corresponding to angle ATQ.
Any angle at the circumference in segment ABT is called an angle in the alternate segment.
Similarly, segment ACT lies on the opposite side of angle ATP. It is also called the alternate segment corresponding to angle ATP. Any angle at the circumference in segment ACT is also called an angle in the alternate segment corresponding to angle ATP. Just to remind everyone, should there be a circle but no tangent, there would not be any alternate segment or angle in the alternate segment. We have learned about tangent chord angle and the corresponding angle in the alternate segment. Now we are going to discuss the relationship between them.
In a circle, ABT is a segment, PTQ is tangent to the circle. Angle ATQ is the tangent chord angle. The tangent chord angle and the corresponding angle in the alternate segment are the same. The theorem is angle in alternate segment. In this circle, ACT is a segment. PTQ is tangent to the circle. Angle ATP is the tangent chord angle. The tangent chord angle and the corresponding angle in the alternate segment are the same. The theorem is angle in alternate segment. There are three distinct points A, B, and T on the circle. PTQ is a straight line. If angle ATQ is equal to angle ABT, then PQ is the tangent to the circle, while the point of contact is T. The theorem is converse of angle in alternate segment.
Now that we have discussed the properties and theorems of circumscribed circles, concyclic points, cyclic quadrilaterals, and tangents, in addition, we have previously learned about the properties and theorems of circles. We can use these properties and theorems of circles to evaluate and prove certain geometric problems regarding circles. Finally, I wish to share with you that so long as we can construct our knowledge, have a thorough understanding and application, learning geometry can be fun.